So far, we have already discussed how to implement the explicit, implicit, or Crank-Nicholson methods in the heat equation generic example. But we can apply the similar methods, the same methods, for the European, let's say, put option or call option pricing problems. So here, let's look at to the example and consider the European put option pricing using the implicit method. And basically, we can approximate each of these partial derivatives in the Black-Scholes basically PDE. So we start with the BS PDE and approximate each of these terms. And notice that this time in the Black-Scholes model and option pricing problem, we have the terminal condition instead of the initial condition. Okay, so this is important. We have a terminal condition. So the initial condition does not exist. I mean, it's the opposite version. And what we know is the final maturity, the payoff of the option at the final maturity. So actually, when we say implicit method, right, these gonna be reverted. It's gonna be opposite of what we have seen in the previous example. And you can notice that, so we have this time derivative here, and all the other terms are evaluated in terms of the time step j. So whenever you see this j here, and this is j plus 1, this means actually this is the implicit method. Okay, but if we had, instead of this j terms, if we had j plus 1 terms for the space derivatives, these approximations, okay, that would be the explicit. Why? Because as I said, it's going to be explicitly calculated from the previous from the future value, because this time we are coming from backward. We are going backward in time. Therefore, whenever we see the j terms, this leads to us the implicit finite difference method. So you can just reorganize this. Once you approximate each of these derivatives like this, then you can approximate, and then you can try to collect all the things that you don't know. As usual, you can put on the left hand side is what I don't know, okay, and everything I know goes to the right hand side, and you can see that the only thing that I know is this fi j plus 1 term, because we are going backward this time. And this is why now this is implicit. We cannot explicitly calculate the left hand side in this case. And here we have these coefficients a, b, and ci values. So these can be calculated for each I value. Okay. But once we have this, the rest is again just like the previous example. And we can write this in a three-diagonal form. You can see we have these b terms, which are coming from the main diagonal. And the diagonal shifted down by 1, you will have ai values. And you can see the diagonal that is shifted by plus 1, that's going to contain the ci values. And remember again the size of this, well, since I'm using here for the space steps, I'm using I from 1 to n minus 1. So the total number of space points is n plus 1 actually. So that's going to be here giving us a matrix n minus 1 by n minus 1, right? Because remember, the boundary conditions are not included here. They are added separately to the first and the last equations. So basically, those show up here. And this is basically the unknown. So this is the values that we don't know because we are going backward again. And these are the values that we already know. So this now becomes basically the same system of equations as we have seen in the previous slides. So you can apply the same technique that we have done and obtain the solution. The only difference is we are going backward. So what about if we want to apply the Crank-Nicholson method? We can show that also quickly. Um, this time we are gonna basically average two things, the explicit and the implicit methods. And you can see that we have now the time derivative approximation is here. And if I write this as j minus 1 and j, that means what we know is going to be the time step j. So whenever you see time step j, so this is coming from the explicit method. And the other parts that contain j minus 1, right? So j minus 1, j minus 1. So these are coming from the implicit method. So whenever you see j minus 1 terms, these are because we are averaging two methods, so these are coming from the implicit method, and this term is coming from the, again, explicit method, and again you have the implicit and explicit methods. So the thing is, again, we just need to collect everything that we don't know on the left hand side, and everything we know should go to the right hand side. Okay, so the left hand side here, and you have the right hand side of your equation. This is the Crank-Nicholson scheme. And you can notice what we know should be all the terms which contain time step j. These are known, okay? All the terms that contain j minus 1, these are unknown because we are going backward in time for the put option and or also for the call option pricing problems. So finally, you can again represent this as a system of equations using the matrix notation. And you can notice that this time we have two different tridiagonal matrices because the coefficients here will go to the first tridiagonal matrix, which we represented as M1, and the second tridiagonal matrix will contain the coefficients here, and that is given in this M2. And finally, don't forget to add the remaining terms from the boundary conditions, and those are given for the first and the last equations in this term G. Okay, so you can see the boundary conditions are given here. So again, different from the previous methods because we are averaging over two methods, the boundary conditions will contain basically two time steps together, and this is the left end boundary, and these are evaluated at the right end boundary. So once we put all these terms together on the right hand side, which contains what we know, this system can be solved. Either you can use the matrix inversion if it's a small scale problem, but the better thing to do is to use the LU decomposition, and we can efficiently solve such systems as we have already done in our previous chapters.